Well, hello, ladies and gentlemen. We're going to continue on with our discussion of properties of pure substances. So today's topic, we're going to round off quality by illustrating the geometric or graphical interpretation of quality, X. So we introduced quality last time, which is the mass fraction of the saturated vapor in the mixture. So we're going to talk about how to interpret that on a TV plot. And then we're going to look at how to calculate properties for supercooled liquids and superheated vapor. We've already talked about how to calculate properties for mixtures, saturated mixtures, using quality. So we're going to move on to supercooled liquids and superheated vapors, okay? And as you might guess, these calculations involve using the tables out of your textbook or your notes. So you need to procure a copy of the textbook or your notes here pretty soon so that you can start doing the homework due next week, okay? Okay, so geometric interpretation of quality. So let's move on to show you how to represent quality in terms of the saturation dome. So we have temperature and let's say specific volume. Let's do the TV plot. And here's our saturation dome right there. So let's say we're on a particular isobar. So here is our isobar. So P right here. So we have some sort of a container filled with saturated liquid and saturated vapor at some pressure P and at some temperature T, let's say, okay? So we're somewhere on the isobar, P isobar. Let's say that our system here, our mixture is at that state on the isobar. So it's a saturated mixture. And of course, let's put in some relevant isocores here. Isocore means constant specific volume or constant volume. So we have specific volume for the saturated mix. That's that right there. And then we have specific volume for the saturated liquid. That's the specific volume for the saturated liquid on the left-hand side of the dome. And on the right-hand side of the dome, we have specific volume for the saturated vapor. Now, quality, we had an equation a little while ago. Quality can be calculated in terms of specific volume as a specific volume of the saturated mix minus the specific volume of the saturated liquid divided by the difference in specific volume of the saturated vapor and the saturated liquid. Saturated liquid, liquid. I'm getting lazy. I don't want to write all that stuff out. Now let's look at how that equation there can actually be represented on the TV plot. So the numerator, which is VSAT mix minus VSAT liquid, that represents this length right here. Okay, VSAT mix minus VSAT liquid. So that represents the sort of green here. So this represents the green line. I guess that's green. Okay, that's the numerator. And then VSAT vapor minus VSAT liquid in the denominator, that's represented by this yellow line, or this yellow distance right here, okay? So, in the denominator, we have the yellow line, and the numerator, we have the green line, or length, or segment, if you like, okay? This distance divided by this distance, take the ratio of the two and you get the quality, okay? So that's a geometric interpretation of quality. By the way, Let's just make sure this makes sense. When quality, let's see here, when the specific volume is when we have a saturated liquid, if we have a saturated liquid, that means we're over here on the left side of the dome. That means V mix is equal to V sat liquid. We're all liquid. And that means that this green distance goes to 0. Goes down to 0, okay? And that implies quality equals 0 over the yellow line, or 0. All saturated liquid. All saturated liquid, okay? So if X equals 0, it means we have no vapor, it's all saturated liquid, okay? Likewise, if we have a saturated vapor, we switch the screen here. If we have a saturated vapor, I guess I better stick with the other side. Kind of going to go back and forth here. If we have a saturated vapor, and that means we're over here for a saturated vapor. So this green line is actually the entire length, which is the same as our yellow line. So for saturated vapor, the green and the yellow line are of the same length. So saturated vapor green equals yellow equals, not implies. The green and the yellow are of the same length, and so that means X, which is your green over your yellow, is equal to 1, okay? So when X is equal to 1, we have a saturated vapor. Saturated vapor, no liquid, okay? So geometric interpretation for quality. The distance from the saturated liquid to the actual state of the mixture on the TV plot divided by the difference or the distance between saturated vapor and saturated liquid on the TV plot. That ratio gives you the quality. It's a geometric interpretation for quality. When you're a saturated liquid, the green arrow shrinks to 0. Saturated liquid, this distance shrinks to 0, and you get X equals 0, or quality equals 0. And when you have a saturated vapor, over here, the green arrow is as long as the yellow arrow, and you get a quality of 1. So that's the geometric or graphical interpretation for quality, okay? And by the way, this goes for specific volume, or I can do specific internal energy. I could put a U here, or I could put an H, enthalpy, specific enthalpy. So this works in general. This is a general interpretation, graphical interpretation of quality. I could put TV, TU, or TH here. Or, for later on, TS. S will be entropy. We'll deal with that in a month or two, okay? So this is a general geometric interpretation, all right? Tell you what, why don't you box this up? This is an important equation. just to give you an idea of how to interpret graphically the quality. So I put a little box around it, okay? Okay, let's move on to properties of supercooled liquids. Properties of supercooled liquids. We now know how to get properties in the saturated mixture region, in other words, inside the dome. How do we get properties to the left and to the right of the dome? All right, so properties of supercooled liquid. Now, let me show you again. Let's put up a TV plot. I could do PV, but I think TV is just fine. So here's our saturation dome. I'm going to be a bit more accurate drawing the saturation dome. I've been a little bit crazy. I'm just making it a hump. In reality, the saturation dome is very steep on the supercooled liquids, on the saturated liquid side, and very shallow on the on the saturated vapor side. So here we have the critical point. So in reality, the left-hand side or the saturated liquid side of the dome is quite almost vertical, almost vertical. And that means that the isobars get very steep as we approach the dome. So here are a bunch of isobars. I'm not going to draw them all. Not going to draw them all, but I'll draw a few of them. A bunch of isobars here, okay? They get very steep. The whole side of the curve is very steep. Whole side of the curve is very steep. And this is true for not only specific volume, but specific internal energy, okay? Yeah? Now, what this means is the following. Given that it's so steep on the left, so saturated liquid side of dome, almost vertical, almost vertical, almost vertical. What that means is specific volume and specific internal energy don't change much with temperature. Okay, they don't change much with pressure, and they don't change much with temperature either. So because it's so steep here, because it's so steep, and these isobars get so close to vertical, what we can say is that the change in specific volume, with respect to pressure, okay, with respect to pressure, is much, much less than the change in specific volume with respect to temperature. Okay? And also, because these isobars are so steep as we approach the curve, because this is true, we can therefore say that specific volume evaluated at any temperature or pressure for a super cooled liquid. So if I want to calculate specific volume on any isobar for any temperature in the supercooled liquid region, that means out here, the specific volume for a supercooled liquid at any temperature and pressure is approximately equal to the specific volume of a saturated liquid at temperature T. So instead of having separate tables, supercooled liquid tables to look up specific volume of H2O for any pressure or temperature in this region. So over here we have super cooled liquid. So instead of having tables here and having to look up for a temperature and a pressure, the specific volume of a supercooled liquid, all we got to do is find the specific volume of the saturated liquid at the temperature T, okay? So I would put a little box around this, okay? Specific volume of a supercooled liquid, in other words, if you're in here, in the TV plot, you're in the supercooled liquid region, is approximately equal to a specific volume for the saturated liquid at a temperature T, okay? Temperature is what's driving the variation in specific volume, not pressure. Liquids are highly incompressible. You can jack up the pressure and not squeeze a liquid down much. But you can heat it up and a liquid will expand and contract a lot. So we're saying that the temperature dependence is much more important than the pressure dependence on specific volume for a supercooled liquid. So we can approximate specific volume for a supercooled liquid as that of a saturated liquid. Same thing is true for internal energy. We can say that the internal energy for a supercooled liquid at some temperature and pressure is also approximately equal to U of the saturated liquid at that temperature. Okay, so I put a little box around this too, all right? Now, one last thing before we move on, we can't quite say the same thing for enthalpy. Remember we introduced enthalpy last time? Enthalpy is U plus PV. So enthalpy is U plus PV. So H is internal energy plus pressure times volume, or if you like, specific enthalpy is specific internal energy plus pressure times specific volume. Now we got to be a little bit careful when we're evaluating enthalpy of a supercooled liquid because we actually have pressure in the expression. So that guy's variation is not negligible with respect to pressure. Pressure is an important input to enthalpy, so we can't neglect pressure variations when we calculate enthalpy of a supercooled liquid. So let's figure out how we get H for a supercooled liquid. Well, H, supercooled liquid, evaluated at some temperature and pressure. How are we going to approximate it? Let me write out what enthalpy is again. So that's internal energy, specific internal energy, plus pressure times specific volume. And this is for supercooled liquid evaluated at some temperature and pressure, okay? Now let's use our approximations that we have for specific internal energy and specific volume. Specific volume for a supercooled liquid approximated as that for the saturated liquid, and specific internal energy for a supercooled liquid at any temperature and pressure is approximated as that for the saturated liquid at the temperature. So let's apply these approximations here. Well, this is approximately equal to U for the saturated liquid evaluated at temperature T. That takes care of the first term. Plus pressure times specific volume of the saturated liquid evaluated at temperature T. So we're using the approximation on the product between pressure and specific volume, okay? So these two terms I'm using the approximation for. The pressure needs to be there, We need to leave the pressure term in there and the pressure in that product. Because depending on the pressure, if it's very high pressure, then enthalpy can be much higher than internal energy if the pressure is cranked up too high. So let me write that expression down here. H for a super cooled liquid evaluated at any temperature and pressure is approximately equal to specific internal energy for the saturated liquid evaluated at temperature T plus pressure times specific volume for the saturated liquid at temperature T. Okay, put a little box around this. Put a little box around that. Okay, so you should have 3 boxed expressions now so that you can calculate internal energy, specific volume, and enthalpy for a super cooled liquid. Let's do an example. Let's do an example. It's a lot of stuff. Let's do an example. Let's see here. I'll tell you what, I think I am going to, let's cut it.